Good morning, everyone, and welcome to the second session of Getting Close to the Nucleus. Our speaker is once again Gilles de Weis. He's an associate professor at the Radboud University in Nijmegen and has written lots of the NMR code over the past 20 to 30 years. Once again, his research interests lie in modeling the behavior of solid-state systems in magnetic fields. And he's going to talk about the NMR features implemented in VASP and also have several examples. So go ahead, Gilles.
Chris, thank you very much. We are going to continue with the second part, which is a little bit more practical than the first part. It's mainly about NMR, but also NMR related properties, but also a little bit on other hyperfine things. But let's start with NMR. A little bit basics of the NMR. So I'm not an experimentalist in NMR, so it will be a very limited story, but I hope to give the essentials for a good introduction. So what it does, it exploits the Zeeman splitting of a nuclear spin. So you see here an energy as function of magnetic field, and the energy levels for here in this case a spin half particle, they are being pushed apart, and this difference can be probed in some resonance experiments in NMR. But the spins that actually you push apart here, the states of the spin that you push apart, those states also depend on what happens around them in the material, in the crystal. So they depend on the physical surroundings and they give information on the crystal. And that's why this is interesting. This otherwise would be a little bit boring. It's just a Zeeman effect and that's it. But there is more to it than this. And what is all in there is to a large extent summarized in an NMR Hamiltonian that will come in a moment. But let's first do this slide. I was already in the next one, sorry. So what is it? It is nuclear magnetic resonance. And it probes the nuclear spin resonance. Levels are split by the external magnetic field, B0 or Bx, whatever we call this. But this resonance is also affected by the surroundings of the nucleus. And part of that information goes by the electronic structure. So you need to calculate some electronic structure stuff in order to model that. That's why, of course, VASP comes into play in the first place. Then the key properties, the effects that will be apparent in this Hamiltonian in a moment, are the chemical shielding. So that's the induced local magnetic field at a nucleus when you put it in a magnetic field. We look at the chemical shielding. We do not look at night shifts at the moment. Night shifts is the same thing, but then in a metal. So where if you put that in a field, you get that one spin channel gets more populated than the other one. You get a local magnetization, which gives huge shifts and shieldings. Okay, chemical shielding. There is dipolar coupling. For that, you don't need the electronic structure. There is J coupling, which you can calculate in principle, which goes via the electrons. And there is the quadrupole coupling related to the electric field gradient. So the J coupling is telling how different nuclear spins talk to each other via the electrons. They also talk to each other directly, but via the electrons. And the quadrupole thing is only possible, of course, if there is a quadrupolar nucleus, and that quadrupole senses the electric field gradient at the nucleus, and that is determined by the structure. Okay. Then another important thing, NMR spectra are effective if things move. And so many interactions are averaged. So the more stuff is moving in an NXPAR experiment, or the atoms or whatever, the liquid or whatever, the cleaner the spectra gets. So it's a very weird technique in a sense. And you can play with that. You can play that removing unwanted interaction. That is done by the famous magic angle spinning. And when you rotate the sample in the magnetic field at a certain angle to the field, any other things of movement. We will see movement also in the illustrations at the end today. This movement, whether that is important or not, is set by the NMR timescale, which is typically megahertz. So if things move much faster, then what you see in NMR gets averaged. and you see a single apparent tensor for each side. If things move slower, you see actually something moving from one place to the other being resolved in the experiment. Okay. Here there are some references. So this is a very famous basic book with many people who start in NMR work through. Then there are some other, this is a good review book. This is a good review paper. And of course, this you can't access, but I did that. In order to get the next slide, so this is the effective nuclear spin Hamiltonian. So let's look what is in there. There's this I here, this vector I, that is a nuclear spin vector. So for each nucleus K has its own vector. Gamma is the chiromagnetic ratio going with that. You also saw that over here already, popping up in the splitting. Okay, then if you multiply the two together, you get a nuclear magnetic moment. And Bx is the external magnetic field, which we also call the Bill-zero field. So then we have this whole term over here. And this is the external field talking directly, this talking via the chemical shielding tensor with a minus over here. It's the first term. But here you see dipolar coupling, the J coupling, and the electric field gradient. First about the units. This is a little bit confusing. In this case, it is in angular frequency units because we have somehow divided by h bar. Again, go back here. You see h bar over here. It has been removed. And you can be make all kinds of mistakes there, and people can make a mess. And I've seen now in the last week a few review papers where indeed it is not all consistent. Now let's look at the several terms individually. This is the dipolar coupling. That somehow is the simplest one. This has to do how one nuclear magnetic moment talks with another nuclear magnetic moment just via the dipolar fields that the nuclear magnetic moments generate. So there is no electronic structure information in there. So you can directly calculate it from this expression. These are the distances between the nuclei. These are their chiromagnetic ratios. That is all what goes in. It's the simplest term in this sense. But all the other terms, they need some electronic structure information. So this is the shielding tensor. That's this one over here. With the identity over here, you just have the B field talking to the nucleus, but additional currents are introduced into the material. We've seen that yesterday, which give shielding fields, and those shielding fields are expressed via the shielding tensor, sigma over there. Then there is the J coupling tensor. So the nuclei talk to each other via the electrons in a very similar way as here with the dipolar coupling, but the physical mechanism is different. And then over here, you also see the nuclei talking to each other, but this via the electric field gradient, which is in this tensor. And up front here, you see the strength of this interaction, and there is this EQ, that is the size of the nuclear quadrupole moment of this nucleus K. So if the nucleus has no quadrupole moment, this term is gone. It is very often the case. But in other cases where this term is present, this can actually be the dominant term in the whole Hamiltonian. You would be careful with that. Okay. And all these things, as it says here, all these properties hold structural information that you hope to get in an NMR experiment. And what we now talk about today is a little bit about how we calculate this one and what it can tell you about the system, what this one can tell you about the system. We briefly touch upon D also when we do molecular dynamics simulations, and we do not touch on J. J can be important, but in a solid state context for crystals, that is often not a very interesting thing to model. In liquid state NMR, it is very good. Then about the notation, well, you've already guessed, of course, it stands below here. This thing is a tensor, so this is a 3 by 3 thing here in Cartesian components. This is a vector, and here this is essentially the transpose vector to make this whole thing a scalar quantity, to make this into a number. Okay, and so this is the NMR side of things. We will not go deeper into that, well, a tiny little bit. We're now going to look at the first tensor, that is the shielding tensor, or the chemical shifts that are related to it. And here we get the shielding tensor again, is the definition we saw yesterday. And we apply an external field. We measure at the nuclear position the induced magnetic field. And it has three components, and this also has three components, so we get a 3x3 quantity. Here with Cartesian indices, but of course you can have different axes, whatever you like. And this is to a very good degree linear in the external field. So you could also calculate it like this. Okay, so you get in principle 9 independent Cartesian components, all different of the tensor. But in an NMR experiment, typically people only are sensitive to the symmetric part of the tensor, not the asymmetric part of the tensor. And very often you only look at the trace. That is the isotropic shielding. And the observables that they get out, they are characterized in a specific way. So what the code does to go there, it first calculates this thing. This is like a 3x3 matrix, essentially. Then it symmetrizes the matrix. So xy becomes yx, xc becomes zx. And after that, you bring it to principal axis because you have a symmetric matrix. You can always diagonalize that. So then you, after that coordinate transformation, you essentially only have 3 non-zero elements on the diagonal. And then you have conventions for reporting those 3 elements. There are 3 of them now. 1, 2, 3. You can order them like this: 1 smaller than 2, smaller than 3. And then you can talk, well, easily about the isotropic one. It is just taking the average of the 3, adding them up and dividing them by 3. That's the isotropic shielding. In this convention, the Hertzsprung-Berger convention, you can also talk about the span, which says you what is the biggest minus the smallest. So this is the complete range of the spectrum that is possible. And it's always a positive number. And then you know what is the average, you know what is the range of the thing. And then the third component can somewhere be in between the outer limits. And then you can measure with the skew, which can go from -1 to 1. We will see also in a moment a little bit more on that. All this is summarized over here. If you talk about these things, you actually say something about the CSA, about how much this thing differs from an isotropic tensor. Okay. Next slide is not the shift yet. Next slide is another convention, which is used still much more often nowadays than this Hertzsprung-Berger. That's the Haberlin. I don't like it so much. It's a little bit fuzzy. But there you first calculate the isotropic shielding, still in the same way. Just the trace divided by 3. And then you order your elements in this way. And then you talk about an asymmetry parameter and an anisotropy parameter, or if you want to make it a little bit more confusing, talk about the reduced anisotropy. I always find it a little bit confusing, but there are, for example, online helps. This page is very useful, where you just throw it in one convention and get it out in another. Okay, so we have 2 conventions now, and I think now we have to go to shifts. And that relates to the experiment. In an experiment, you don't measure this absolute thing like the shielding, but you measure the difference between the shieldings in 2 systems. You look at the system you're interested in and you compare it to a reference, some system in a very well defined state, of which you know everything, have everything under control. And then you look at the difference between the shieldings in those 2. And that is the chemical shift. And that is in this formula over here. So this is the first measurement you do on a reference system, a standard system, very standard conditions in your spectrometer. Then in the same spectrometer, you study the system you're interested in, the nuclei you're interested in. You also obtain an isotropic shielding for that. And the difference of the 2 So then the zero of these doesn't match and it drops out. And that actually gives you the thing called the shift. And the shift, you see, it is positive when the shielding has a minus sign over here. So that makes for kind of confusion. Yes, this I all said. To talk about the confusion, here it's summarized. This is how spectra are often reported in the literature. The shielding always increases when you move to the right. So this means that the shift always increases when you move to the left. And very often you want to have an axis with the shift, so you go from minus to plus. And then you have conventions that go back from the days when the NMR magnets work different as they do now. And if you know how those things work, but I don't know, then you know that on the right-hand side you move upfield, and on the left-hand side you move downfield. So this is kind of a thing to interpret how all those things are related to each other. Okay. Now, when you do a calculation, you also need to reference somehow. And you can, of course, do the same thing. Here you have the formula again for the isotropic shift related to the isotropic shielding. But now you could take the experimental reference system, do a calculation for that, and in this way just calculate this shift. So also comparing two experiments. That's of course a perfectly valid way of doing it, but you can also do it in a bit more robust way, and that is by a fitting procedure. So you have for a whole series of materials, you know what are the experimental shieldings, for example, along this axis. And for this whole set of material, you calculate your shielding, and then you just do a fit. And you hope to get out a straight line with slope -1. This m should be 1 here. And then the other fitting parameter is then, of course, the reference shielding. This is a very good way of doing it. Often I do this, but this is, of course, the proper way of doing it. With this M, you can, for example, adjust a little bit for kind of the level of theory you have, which function you have, gives a slightly different slope. Also depends a little bit on the nucleus. The deeper you go, the more difficult it is to actually get, the deeper in the period table, the more difficult it is to get actually the slope of -1 over here. This is just an illustration for fluorine in this case with many solid state fluorine systems calculated against experiment. A little bit more on the detail there. Let's first simplify a little bit. If you have a spin-half nucleus, there is no electric quadrupole to mess up your spectrum. And you could, for example, look at hydrogen. And one hydrogen has no quadrupole, deuterium has, but normal hydrogen doesn't have. And then if you do a static experiment, so you don't spin the stuff in the NMR machinery, and you do a lot of damage to your material, you make powder, so that you get grains. And in these grains, all orientations of the tensor are present. And then you could, for example, see something like this. This is a simulation. But if all orientations of your tensor are present, you see them one, you see the maximum, and you see the minimum. You see, of course, also the other in between, but you see also all the other stuff in between in the whole range. So you see the span over here, but you see also all other tensor orientations. Okay, if you now spin the thing, so you have a rotor in the NMR magnet, you put it at a certain angle to the magnetic field in this way, and then you have it fixed at that angle, and then you start spinning it around the axis, which has this orientation. And then you start averaging all the orientations, and you start to see the isotropic shielding emerging in the spectrum. So you spin harder and harder and harder, the spectrum shrinks, it goes to almost one peak, you hope, and then you find this ISO. And so that's also why this ISO is the main interesting thing. Of course, you get all kinds of Fourier transform trouble and whatever, but that is for the experimentalist. But you see the ISO is important. There is also dipolar couplings, which are not in the spectrum. But by spinning, you actually can also remove those. That's one of the big actions for that. You can also remove the particle polar interaction, but not completely. or only in some approximation, but certainly not completely. But for hydrogen 1, this is not an issue because it has no quadrupole. And then why a powder? Like the NMR people always, well, they need a lot of signal. They need many nuclei to have sufficient sensitivity in their machine. And many crystals, you cannot make that big. So that is why there is a bias towards using powders. All small crystallites that are, say, oriented in many different ways. Now an illustration why these shieldings are so important. This is just one example done in the solid state chemistry group over here a few years ago on crystal of this antidepressant drug over here. And you see all the carbon sites in here, and then they spin and they do something to enhance the signal strength. And then you look at the 13 carbon spectrum and you see all those little peaks, and you can say exactly who is who. There are all kinds of rules for interpreting this, and you can also play with the interactions here to see who's next to who. And if you don't know that, you can actually do a calculation. But this is very useful. If there is a polymorph, which is slightly different, then the peaks change, and you can identify this, or if a group rotates to another orientation, you can actually see this in where the peaks are sitting. So this is the typical game. You measure and you play who is who. A little bit about quadrupolar nuclei. Here, the spin has to be larger than 1/2. Yeah, this is nonsense, this sentence. It says only nuclear spin larger than 1/2 is non-vanishing EFG. That is not true. The EFG is always there, but only then you can actually measure it in NMR. We already saw this tensor yesterday. It's traceless, and you have two values that characterize it. The biggest one, which goes into the CQ via the quadrupole moment, and the asymmetry parameter. And here you see a figure for a spin 1 nucleus, where the spectra are plotted for several values of eta. You see the range. The range is always set by the CQ value, so that is a way to see the CQ from the spectrum. And the shape determines your eta. So eta 0 has this two blobs over here, and then it goes down. Eta is 1 and eta is 0.5, have very different shapes. It's not always as simple as this shape. This only holds for the spectrum described in first order perturbation theory. To get it correct, you need second order perturbations. They always give a finite width. And that is also the reason why you cannot spin all this away. And if you combine a CSA spectrum, so chemical shift stuff, with a quadrupolar effect, then this gets rapidly more and more complicated. And so you need to do spectral simulations. It's an art in itself, and it depends on, say, on the spectrometer and the kind of experiments the experimentalists do. That would all go far too far, so I will not talk about that now. I will go to a next slide, which we should go over rather briefly. There are a few undocumented features in VASP. There are only 2 slides on this. The first slide is to arouse your interest, and the second slide is to take care that you don't try to use them because it's really difficult to use them. But the first slide tells you about another way that you can actually calculate the shielding tensor. And the shielding tensor you see over here. And what is it? It is you apply an external field and you see what the induced field is. So this part is the shielding tensor. And this delta is just this thing over here. But if you now look at this derivative, you can see, okay, what is this in, what are these fields? These fields have to do something with an energy when you bring a magnetic moment, say the magnetic moment of the nucleus, inside the field. If you do m times b, you get minus e. This is a simple formula from electrostatics. So you can see that this term actually, you can write as this derivative with the minus. And then you can do it change of derivative order. And then you can play the same game. You can go now here with this external field to a magnetic moment again. A magnetic moment is a magnetization times a volume. It's again a magnetic moment. And then you see that here you have a magnetization, and you take the derivative with respect to a magnetic moment. And then you rewrite a little bit, and then you push this apart again, and then you can see the red thing over here is this red thing. So you have reformulated the problem. The chemical shielding now is not expressed as the induced fields in the present of an external field, but it is expressed as the total magnetization in your system when an ideal magnetic moment is placed at the nucleus you are looking at this nucleus R, where you want to know the shielding. And so this gives a different recipe for calculating shieldings. What you do is you go to the nucleus and you put there the vector potential of a ideal magnetic moment with some size of moment. And then you apply this as a perturbation. And then you calculate what the induced magnetic moment comes out. This is just the definition of the magnetic moment. This is your induced moment. That's this ratio over here. And then you also have a way of calculating the shielding. This is called the converse approach to NMR shielding, which is introduced by Toonhauser. That's Davide Cirasoli and David Vanderbilt and many others in this paper in 2009. You can also use that to calculate shieldings. And for molecules, this is a very straightforward way because you can apply this and you can just measure this. It's independent on where you choose the origin, because at a certain moment, when you're outside the molecule, J vanishes. And if you choose it suitable, the origin of R, you can even get converges pretty rapidly. So for molecules, this is a good recipe. For infinite systems, this is difficult. You start to introduce currents, induced currents by this vector potential. Those currents flow in the vicinity of the nuclei, and at a certain moment they would die out. But all this has to be captured by this integral over here, and everything has to be really zero beyond the edges of your integration range in order to get a meaningful moment. And that is difficult in a periodic system because this is applied periodically. So your supercell must be really, really large to do this. And so the better way of doing this is using this expression, which is the so-called modern theory of magnetization, which is similar to the modern theory of polarization, where polarization becomes a Berry phase. Here, magnetization doesn't become a Berry phase, but becomes something very, very, very complicated. You see, you have an Hamiltonian, you have the eigenvalues, you have to add them. And then you have to sandwich that between k-space derivative of your block states, of the, say, the cell periodic part of that. You have to actually do those derivatives. Then there is a vector product somewhere. And then you take the imaginary part and you sum over everything that is occupied. And then you get this magnetization, this M. And that is rather unambiguously defined in this way. If you don't do it like this, you might have problems with the origin and you measure currents in the wrong spot. For example, if you have a polarization, you know, if you measure a polarization in a unit cell, depends on where you choose the unit cell, what comes out. If all the charges are distributed throughout the whole unit cell. So there you have to go to a Berry phase expression to get that well. And the same holds here. This actually builds on a derivation in this paper, for example, where they go to a Wannier function picture of localized magnetization and then transform it to this block picture. Okay, that is present in VASP for infinite systems, but you cannot really use it. That's a little bit of a warning. So what are now the undocumented features? It is the implementation of the NMR shieldings with the converse for infinite systems using this crazy formula. It follows this paper essentially, but it only works for norm conserving potentials. And the standard ones are ultra soft. So there is a warning here. Even if you find how to use this, don't do it because you will make nonsense with this. So don't do it. Other things which are present is, again, this recipe, but then using this, this direct definition. This direct definition is suitable for finite systems. And it can be useful if you want to do very large clusters or molecules with many atoms, say a few hundred, and you run into memory problems. So maybe we should revive this and actually make this more user-friendly accessible. But it is not documented and it is difficult to use because sometimes it works, sometimes not, depending on what you are doing with how you're steering it. There's also a finite field implementation there which use the direct way. So the shielding is calculated as this derivative. But there is no advantage of using that at all. So the message is essentially the linear response theory, which you switch on with this incard tag, is always equally good or better than this, is always equally good and better than this. Only if you have very large systems, you might want to do this, maybe. Only if your memory really doesn't help you. Okay, so far about the undocumented features. Now again to how good is it? So benchmarks. So we compared essentially to what others calculate in molecules, other codes, and in crystals. And for molecules, we have to make periodically repeated supercells that are sufficiently large so that the molecules don't see each other, that the fields produced by the currents in one molecule are very weak when they're measured at the next molecule. In the calculations you see in a moment, we did this with non-relativistic potentials, purely non-relativistic, because the quantum chemical calculations there are purely non-relativistic. So you can very directly compare. And these V2K for potential calculations are also non-relativistic in that case. For the crystals, we didn't do that, but for the crystals, you see shieldings and susceptibilities. Magnetic susceptibilities are needed when you have to account for the shape of the crystal ice, for the surface currents that flow onto this, giving small contributions to the shieldings. Okay, we never relax geometry so that everything becomes really comparable. It's always PBE now. And you see what happens with simple standard for podcasts and very accurate ones where you try to optimize things. These are a few references of the V2K implementation and the quantum chemical Dalton code. Okay, and here you see for molecules, you see an old list of calculations. The units is in ppm. It's VASP, it's quantum chemical, it's V2K, and it's all non-relativistic. And in quantum chemical calculations, you can very systematically improve the basis set going from double central to triple zeta to quadruple zeta to quintuple zeta. So this is the worst, this is the best basis set. You see here, there's not much difference. Over here, you see a lot of difference going to better and better and better basis sets. Also, these are uncontracted data. Otherwise, there is no systematics in this stuff, unfortunately. And then you can compare it to the Win2K. So this is the best Win2K results. This is the best VASP results. And this is the best Dalton results. And you see over here, it's rather very good. It's always good in the shielded limit. So on the top with the high shieldings, but in the, say, the de-shielded limit, it is always more difficult to get to very good convergence. It is still all pretty good, but to really hit it is difficult. For example, look here at F2. We're very close to Win2K. This is not the same. It's still maybe not fully converged. You actually don't know. Okay. But these are very good potentials. If you take the standard potentials, it also is pretty decent already. All the trends are there, all the differences are pretty okay. But for example, here you can still have a big effect, say of almost 20 ppm over here. But you have to compare it to this difference. This is more than 400 ppm. So also with standard potentials, you come quite far. That's the message also here. So you see here this works. Then we go to solids and the molecules. The solids we compare to the full potential within 2K calculations and the VASP implementations. There are also a few other calculations listed over here. And we can look at the shieldings and we can look at the susceptibilities. Now this you will also see in a moment summarized in a plot, so we'll not look too much at this. We have a look here at the susceptibilities. Note that is in a different unit. And we'll also later talk more detail about it. This is the PGV approximation. And here you can compare it to the Wien2K numbers. Often it's good. Occasionally there is some kind of a problem. But in general, this approximation works pretty well. We now also have the VGV approximation, which is better, but we don't have recalculated for this set. This is for fluorine, that's the most difficult one. This is for oxygen. This is already not in the upper right corner of the periodic table, so slightly less complicated. You see that performance throughout is now pretty good. And here you see the numbers of the two previous slides actually summarized. This is the all-electron Wien2K results that we use as a reference here. Over here you have the VASP results. And if you have the red spheres, the red circles, that's just with standard PIW datasets, standard podcasts, and it is already pretty good. Unless maybe over here. And what is this? This is cesium and barium. So these are systems with very shallow semi-core states, which very easily polarizable cores. They're very difficult to handle. But if we go to very high quality potentials, we can also handle that. That is the black circles over here. Also optimized PIW datasets. This is theory against theory. That, of course, must always be okay. But you also want to look at how this goes against experiments. So here you see the trick that we've seen previously, where you want to do the referencing trick. You do the experimental on one axis, you do the calculated on the other axis, and you just try to do the fit and see how well it fits. And here you see that the slopes are in fact and not completely -1. And they are dependent on the functional. This is all PBE. You get a specific slope in here. For oxygen is 0.86 or so. And for fluorine, it's about, this is with the good potentials. This is the best result. What is noticeable here is that this calcium drops out. People have studied calcium in more detail. This has to do with where with the simple semi-local functional the D states are. They are too shallow. So that gives rise to a shift which is a little bit off. You can repair that by playing with your potential. Did I forget anything here? I don't think so. Yes. So this is the standard story. Now we're going to look at some improvements that are occasionally important. We saw this also already yesterday in the calculations of the shieldings. What do? Suppose you want to know the shielding at this nucleus 1 over here, the red one over here. You calculate the induced currents on the plane wave grid in your system, which is also periodically repeated here. You just see 4 unit cells of the system, so you have it over here. You calculate with Biot-Savart of all the currents that go in here. You calculate the field over here, and then you have to do a 1 center correction to restore the detail, all the electron detail inside this sphere. You do this. And then typically the effects of the other spheres you neglect. But you can introduce that. You can say, okay, also here we do one center corrections here and here. And those augmentation currents have an influence on field over here. In a very good approximation, very often, you can neglect this. But in the case of hydrogen, that's a little bit on the edge. And there you can actually improve it when you include these contributions. And how should you do that? That is outlined over here. What you can do is you have this currents here, which you describe with spherical harmonics times radial functions. And it is very difficult to get the effect in that local basis over here. But what you can do is you can do a multiple expansion of those currents. And the multiple expansion of those currents, you can mimic with very soft multiples. And those very soft multiples give the same multiple expansion. You can represent on the plane wave grid also. So you throw all this information on the plane wave grid, except for this one, where you throw it on the plane wave grid. And then when you do your Biot-Savart, you get all these effective two-center contributions when you calculate the field over here. And that was already in this paper. But to demonstrate the effect of this, we compare to very accurate quantum chemical calculations, which are done for molecules necessarily, where they have actually reached the basis set limit. So they have absolutely converged numbers. That is this paper by Jensen. And in the next slides, we are going to compare to this. And you see here the effect for hydrogen. So this MW6 multi-wavelet at some certain level from this paper is over here for all these funny little organic, like whatever, molecules at the top of the periodic table. And then you see if you calculate without this two-center effect, just the shieldings, and you plot one against the other, you don't get this straight line with slope 1 over here, but you get all this scatter over here. And for these crazy molecules, which are really difficult molecules, with strong bonds, with nuclei coming very, very close, you get significant deviations. So that is not good. If you switch on this effect, so also account for what happens in the others, and then that you see over here, then not accounting for it is the open circles. Accounting for it is the red and the green spots. You restore very, very good agreement with these two center effects. Here we also tested the effect of the cutoff. Of course, 4000 dV is completely ridiculous. 900 is already ridiculously large. This is just for the benchmarking purposes. You see this, it doesn't really matter, just to be absolutely sure. How you can use this, you have to go to the NMR and switch it on. The default is switch it off. And it's not a good idea to always switch this on. You only need this in special cases. In special cases is hydrogen coming very close to something else. That is 90% of the special cases in which you might need this. That's hydrogen. And indeed, let's look, for example, at another nucleus. Let's look at carbon. So in carbon, if we would make the similar plot here, we could get carbon here, 200 ppm, carbon here, 200 ppm range. We just get a straight line, we don't see the difference. So what we have to do, we look at the carbon shielding range over here, and we just look at the difference between what we calculated and what it should be. And that we plot on the vertical axis. And then without any funny corrections, just a simple one center approximation, you get these black open circles. That is already pretty good. It's a 1 to 2 ppm range scatter on 200 ppm. And now if you switch this on, you get the green stuff. That is now very nice because it is flat. It is still some offset of what it should really be. But who cares? Because differences are always good now. And then if you do the crazy thing with 4000 dV cutoff, you get that things are actually fluctuating around zero instead of fluctuating around a constant a little bit above zero. But this makes no sense in any applications, no gains. So now let's talk about doing a calculation in linear response. Actually doing a calculation. You need 4 files when you do a VASP calculation. Incar, K-points, postcar, podcar. It's like always. You can do without K-points if you specify something in Incar. You get output on outcar, you get output on postcar. Let's have a look over here. Doing a calculation, postcar. Postcar is just standard. The messages, there's nothing special here. This is, for example, diamond in a primitive cell with two atoms, this one and that one. Nothing to worry about here. Only if you, for example, have an organic crystal and the people have guessed where the hydrogens are, optimize the hydrogens if you want to work with experimental positions anyway, because they have guessed them and you get very strange numbers if you don't optimize them. That's postcar. K-points is also nothing special. You need to specify a mesh, but the mesh has to be sufficiently dense. And typically, it should be better than what you need for the other standard stuff, for structure, forces, and energy. If you optimize that stuff, those properties, often you need a slightly denser mesh for the shieldings. So the messages test convergence, and the other messages look at how you choose this depending on the symmetry of your crystal. That is now very well explained in the wiki. We continue with podcar. That's the potential. How you get that depends on how you access the database. In the example here, it's just the carbon with the PBE. But what I want to say is be careful to have at least the minimum required by the recommendations. That's the bold waste one in the available list. But often that might not be enough. This might typically not be enough if you look at something with the field gradient, if you look at something hyperfine, if you look at zero field splitting. In those cases, you might need actually more. You might need semi-core stuff more fast. In case of doubt, try and test. Be careful. That's the message. And if you have very short bonds, you might need the hard potentials, double or whatever. And then it is advisable to use LLRO. In fact, for any organic crystal, it's advisable to use this. We'll always slightly improve. Okay. Then the Incar. So this is from the wiki. It looks like that for the past few years. You see here everything. You see 2 blocks. These are the tags specific for doing the shielding calculation. These are general tags. So let's first go over this block. If you have L-GMAC equal true, you switch on GPOL shielding. So you don't say L-GPOL equal true, you say L-GMAC equal true. Then there is DQ. This is the size of the Q-point stars that we talked about yesterday. And there is a default, and very often the default is okay. You don't have to touch it in most cases. Then there is IGBR. That has to do with the susceptibility. It's how good you do the second derivative in the susceptibility, which is also has to do with the stars. The default is very often more than enough. So typically, you don't need to touch this. You don't touch this. You don't touch this in the general case. Then the third one, that is very important. That is the NMR sim red. That does, again, a simple symmetry analysis on the Brillouin zone, where now not only the points in the irreducible parts have to map onto other points, but also the stars have to match. So the Q-point stars map onto complete Q-point stars under the available space group operations. This enforces this. And the default is false because it's faster. But it is much safer to switch it on. So this is a tag which might require care. And it matters how you represent your crystal in POSCAR, what this is going to do. If you do this, very nicely symmetrically set up along the crystal axis, because this is the first reciprocal basis vector, this is the second, this is the third, then you reduce very efficiently to the irreducible part. But if you make slight rotations of these vectors, the Q stars are always along the real Cartesian axis. If you make slight rotations of this, you might end up with the full Brillouin zone scan. So you need to take some care in setting up the POSCAR. Then the last thing is the NL spline. And this has to do with POW projectors in reciprocal space. This now has to be K-space differentiable in a sense because we go on these Q-point stars with finite differences. And in real space, so when L real equal A, this is always the case by default. So you don't need this. So this combination doesn't make much sense. But when you are in reciprocal space, so this default for your PAW projectors, it might be advisable to switch this on. You notice it much more in the susceptibility than in the shieldings. In the shieldings, the bare shieldings itself, it's a small effect. Okay, so this was the first block. Now we go to the second block, doing a calculation for the shielding. That's the upper block, is the general standard tags, precision, ENCAT, EDIF, all that stuff which is set over here. Be careful with key and cut. Never use less than preg accurate. This might be a little bit more than the actual default. Do some simple tests before you go to a big system. And this EDIF should be much tighter than usual. Also, take care in doubt, but I would at least use this. Then smearing. We're working with insulators, semiconductors. Otherwise, there are night shifts. We don't have night shifts here. We're working with a system with a gap. The linear response, to work correctly, should have all the occupied orbitals completely occupied and all the empty ones completely empty to a very large degree. So if in outcar you see a Cation state with, say, occupancy 0.001, it's not good. If you have E smear equals 0, which is the Gaussian one, then your sigma was too big and you should make it even smaller. So reduce it in case of doubt and use Gaussian smearing. Another bloop. I don't, okay. Then, yes, L real. You can use real space projectors. Okay, it works. If you are in a reciprocal space, you could use this L spline. I've already said that. But you don't need to use this. You can switch this on, you can switch it off. Other tags that are not here and which are NMR specific are the LB1, which next to the big component also reconstructs a little bit of the small component in a scalar relativistic calculation. It's a small effect. Typically, we don't use it, but you can do it. You have this two-center thing. I already discussed that. And you have what you use for your susceptibility. It can be the VGV, it can be the PGV. There are also new tags, they will come later. Okay, doing the calculation, let's have a look at the OSTICAR. When it starts, you start with an SCF, optimizing everything to a very high degree. And never mind if this is too small to read, it's about the general idea. And then you're converged. And then in the shielding calculations, you go onto these K points on this star, this Q point star or K star around the K points. So you have to move away and you have to optimize your orbitals again. You're doing Davidson optimization, but without being self-consistent, with the field applied in one specific direction. Once you are on this Q point, this K plus Q point, you do the Sternheimer, you do the response calculation. Do it once, and then you're finished. And then you go to another point, and there are 6 of those. So you go 1, 2, 3, 4, 5, 6, and then all those points do a Davidson and do a Sternheimer calculation. And then, meanwhile, after the 6th point, you're already on the next slide over here. Then you go to the central point where you already know everything, so you don't need to do a Davidson, and you do again an optimization. Now not called the Sternheimer, not called RMM, but called RLQ. And after this, you have done 7 of those for one direction magnetic field. Now you do another one in the Y direction and another in the Z direction, giving you 21 in total. So you can get a feeling of how far you are. If you are here and you've done only 2 of those and your CPU time limit is almost finished, then you're never going to make it. So you can plan a little bit. That's the OSSI card. Then the out card. And the out card gives the complete tensors, 3 by 3 tensors, and the orbital susceptibility, but the data is all a little bit scattered. And so we will make this better. There will be a new output soon, and we will glance at this in a moment, but first discuss the current old-fashioned output, where the important stuff is being summarized. So we only focus on the summary part now. What happens there is the tensors are built, the tensors are symmetrized, and after the symmetrization of the tensor, we calculate the shift or the shielding, the span, and the skew. And we do it in 4 different ways. You see 4 blocks over here. You can either do it with the frozen core electrons included, that's over here, or excluding the frozen core electrons, just a rigid contribution being added when you go from here to here. And what you can do is you can do it excluding a GH equals 0 contribution and including it. So excluding a G equals 0 contribution is you don't take care of the macroscopic surface currents that flow over the surface of your crystal. Including it, you do take care of the macroscopic surface currents floating over the surface of your crystal, and it are typically small effects, a few ppms that this does. But this is important for crystals. This is important for molecules because molecules do not have a surface. Well, the crystal of infinite molecules, the infinite crystals of dilute molecules that we have over here doesn't have a real surface. That's the message. And so for molecules, use this. For crystal, use this. Or if you don't use it, think why you don't use it. That's one part. That are the blocks. Now, the things that are reported over there. Something called ISO shift, something called span and skew. We already seen the span and the skew. Here you see what actually is reported. The ISO shift is minus the isotropic shielding. So it's actually minus the shielding that you see here, minus the isotropic absolute shielding over here. So minus, put minuses in front, you get the shielding. And this is a little bit awkward. This also has been a reason for confusion in the past, and that it is here also is due because of confusion. It would have been better to just have the shielding over here, the isotropic shield. But if you have this definition of iso shift, if you would add the reference shielding to what you see over here, you would actually get the real shielding. So it makes sense to in some way. And further, it's just Hertzfeldberger that is reported over here. And this is really unambiguous, like it is defined in this paper. Okay. Now the new output. In the new output, which you need not have, but which will come in a new release, we will not make a separate report to the contribution without core shielding. We always include the core. So this first block over here is just gone. But the second block, it's still there. But the second block is now reported after the total shielding tensor has been reported. So what is this? You still have G equals 0 excluded or included. But here you see the full tensor, not symmetrized yet. You can't see that here, but it is not symmetrized yet. Then it's symmetrized. And after that, we calculate the shielding. the span, and the skew. As you would expect intuitively, the program would actually report. That's the new output. Okay, it's good to say that, I think. Okay, illustrations on diamond is also in the hands-on, but it's slightly different here. This is the old LDA thing. What we want to show here is you increase cutoff, cutoff, cutoff. The default cutoff here is 414. You see at 414, you're actually there, but you're on the edge. You're very much on the edge. So it's dangerous to trust the default. It is good to go a little bit over, to test a little bit. 800 is overdone. Well, it depends what you want, how curious you want to have it, but it's a warning. Be careful with this. The other thing is K-point convergence. Here you see how the shielding goes with K-points. So at 0, you attain the limit at the 20 by 20 by 20 mesh. So you already attained that much more earlier in carbon. But for the susceptibility surface contribution, you go slower. Typically, that one converges slower. That is almost always the case. This one goes slower than the shielding itself, surface contribution. And here you also see it's quite big. For carbon, we calculate about 12 ppm. Typically, it's smaller. Typically, it's on the order of 5 or so. Okay. So now we have to go to applications. This application is nice because it illustrates two things. It illustrates nuclear-independent chemical shielding, and it illustrates ring currents effects. And this is an old calculation that we did, well, Pega did, on a molecular crystal, and in this case, a polymer. We have a polymer here. This is this PPTA. And this is an important ingredient of a high-performance Twiron Kevlar. It depends on where you buy it, whether it's called Twiron or Kevlar. It is this unit repeated, because it's a polymer. And you have rings in here. You have aromatic rings. These aromatic rings, they function like little coils in the NMR. So you get ring currents in here. And these ring currents are sensed in the shieldings of the elements on neighboring chains. They feel these ring currents. So that's how you can look at the packing of this material. That's one thing. And the chemical bonding can be illustrated here with a Nix analysis. So now let's look at this. You can actually pack this material in very, very different ways. You can pack it in a herringbone, or you can pack it not. When you in a herringbone, you look from the top, you see a herringbone. But you can also pack it, but the groups are just parallel to each other. You can change the orientation parallel, anti-parallel of those little bonds over here, of those OH and CH groups. You can have like and unlike vinyl rings next to each other. And you can shift a little bit. This doesn't come from elsewhere. This comes from a thorough analysis of how these materials can pack, but that is not really the subject here. You see there are this is 2 times 2 times 2 times 2 is 16. And there is even another possibility. There are 17 different models of how you can actually pack this. And what can the NMR now say? Well, you can do an NMR experiment. You get these peaks. You get a spectrum for carbon here, and you get a spectrum for hydrogen. Which is which? Well, first you can do a computation, and then you can say, okay, these SP structures here, they are energetically so unfavorable that we can rule it out. We can even, with the normal van der Waals functional, you can already see this. But for all the other ones, you actually don't know. You are at the milli EV per atom region. Who is going to be there in the actual fiber material? And there you need to compare your experiments with your calculations. And you can do that. You can do for all the models that you have. You can take the calculated ones, you can take the experimental ones, do the fit, and see how good this fit is. Here it is for one model, but you can do this for all 9 models. And you can get M and you get B. And once you have done those fits, you can look at how well this match experiment. You can define a root mean squared error where you compare the experimental and the calculated ones. And then you see very nicely that some models actually, well, for carbon, every carbon is rather insensitive, but for hydrogen, some models actually do not match at all, and some models do match very well. And this is the ring current effect that does this. This is actually that the hydrogens are in front or not in front of such a ring where they sense this effect. They come very close, the hydrogens, to the neighboring change, and they sense this ring current effect. So in this way, you can throw away half of your systems. You can make this more beautiful with all kind of tables, but this doesn't add anything to the story. So we will now move to a bonding analysis that you can do with the NICS. And next is the nucleus-independent chemical shielding. What do you do here? You take the crystal. The crystal consists of molecular change. If the molecular chains do not have any interaction at all with each other, then you can say, okay, you can calculate the shieldings in one chain. Then you can quasi remove that chain from your material. Then you get a void. Then at the position where the molecules would have been in that void, you can calculate the shielding due to all the other chains. That is then done with an X, with the nucleus-independent chemical shielding. You add the two up, and you would get the shielding of the full crystal calculated. That is if there is no chemistry going on between the chains. But if there is any chemistry going on, you get another term here. You get this interacting thing. So these two added together is different from that one. And that is in the next slide, where this interacting is reported for a few of the hydrogens. So we take one model, or we take a series of models over here, and calculate this delta interacting for the hydrogens. And then you see that for several of the hydrogen positions here, nothing happens. But the NH hydrogen, which is involved in a hydrogen bond with the next chain, that gives a huge thing. That gives a delta interacting of almost 2, 1.5 in this case. So this is a signal for chemistry going. The 2-1, notice the hydrogen sitting over there, also has some effect with some non-zero effect. And that you can see as an indication of a sigma pi, very small sigma pi interaction where the hydrogen over here pushes into the pi system. This is also a pi system, of course, of the adjacent molecular chain. And so this offers two ways to analyze the systems. Next story. Now we go to the magnetic susceptibility. I have already heard quite a lot of it. So now how to calculate this thing. You have to remember, one needs the susceptibility to get the microscopic surface currents that flow on the surface of the crystallized sensitive zero field, and you can then add it to the shielding. This was, we had this picture yesterday showing this. Okay, what is it? It's the second derivative of the total energy with respect to the magnetic field. So you see it's a double derivative again, but now twice with respect to B. And there is an all electron theory for that, formulated by Maury a very long time ago, for crystalline systems and for insulators. This is not the susceptibility of, say, ferromagnetic iron or something like that. This is the orbital susceptibility of an insulator, which is very often a diamagnetic thing. There are now first and second order changes with respect to the field of H. And if you read this paper, you find many things that you also find in the shielding calculation. And you also find an F-sum rule, you find all kinds of difficult things, technical details that we don't have time for now. The point I want to make is that when you go to GPO, you use an approximation to the actual expression, which has the form of the momentum operator times the Green's function times the momentum operator. But for GPOL, you see it on the next slide. You have this possible approximation and you have this possible approximation. This is the original one. And later on in this paper, this one was also. And here you see how these expressions look like. You see a finite difference. Again, in reciprocal space, this dq comes back over here, but now it's a second order stencil that you actually have to calculate. And this is the PGV expression, where you see the momentum operator here and the velocity operator there. And the velocity operator is a commutator of the Hamiltonian with R. And in the all-electron limit, those things both just become P, and you get the proper expression. In the VGV approximation, you have a V on both sides, and it also has the proper limit. And this one is more accurate than this one, we will see in a moment. Both have the proper all-electron limit. If you make your PAW sets really, really complete, they both go to the correct numbers. Certainly this one does. But it is still not a nice full PAW expression. NL spline, we mentioned, can be important here, so that reciprocal space operators to be differentiable in the second derivative, this can play a role. Also, you can approximate this better with more displacements in Q space even, controlling the Ichi bear. In practice, you don't have to do that in most cases. Okay, let's look at how good this is, PGV and VGV. Again, we're going to compare to molecules. Molecules don't have a susceptibility, but they have a magnetizability of a certain molecule. And that we can calculate from these susceptibilities for the individual molecules. And we can do a comparison, again, to these basis set converged results. And that you see over here. With standard PAW basis sets and with the very accurate ones again. And the PGV expression is the green one, the VGV expression is the red one, and you see a systematic increase. And here with the good data sets, you see an even more systematic increase. You see that ozone is a very nasty guy, it's completely wrong over here. Ozone in PBE is paramagnetic, so it's very strange. This is all biomagnetic, but this is paramagnetic. Completely bad here. With better data sets, it becomes better. If you really work very hard and make your PAW data set really complete, you can actually reproduce it. You should get 184 and you do get 184. Well, there's a very tiny discrepancy. Here it's summarized in the table. In VASP, now when you do a shielding calculation, the PGV is typically used. That is, say, how it traditionally is. That is the Yates-Pickard-Maury paper where the method was introduced that we follow. But the VGV is also there, and you can also have it applied, and you get slightly better numbers in general. Okay, there is more about the magnetic susceptibility story. Exactly what I said just now. You see over here. So it's automatically done, but the default is PGV in applying it. But both are calculated. You have the PGV tensor over here, you have the PGV tensor over here, and notice the units. These are crazy CGS units, centimeter square per mole. To apply them in the shieldings, you first have to convert them to shieldings essentially, and then add to the bare shielding results. And for the VGV, it also reports the principal axis. This one is applied. If you want, you can apply the VGV. And then you also see where it comes. On the left, it's not added. On the right, it is added and it is uniform throughout. So the difference between this column and this column is a constant. This difference is the same as this difference over here. And here, well, here's the point contribution added. This difference is this difference. Okay, this is for molecules when it makes no sense. This is in principle for solids in most kinds of experiments, I would say. Okay, now we get to applications. For the electric field applications, I will only discuss the aluminum sulfide now, and then I will immediately go to the hyperfine stuff. aluminium sulfide. There's a whole zoo of systems. What is nice here what is interesting here is that these two crystals, they're both hexagonal. The alpha phase, the aluminium is tetrahedral coordinated by the sulfur. In this funny TBP, it's also the case, but there is also this penta coordination with this 5 around. This is very weird. And we're going to compare those two now in experiment. And experiment done by Hong Tao, and then calculations done by Shrestha. And you see here, you can calculate the shielding tensor, all its properties. You can calculate the EFG, and you can bring them onto principal axis. You get different principal axis systems. Of course, there are Euler angles connecting those. So all this information is there. When you look at aluminium sulfide, first thing to notice is that the EFGs actually are non-zero. If this would be a perfect tetrahedron, the symmetry would be perfect and the EFG would be 0 if this is at the tetrahedral symmetric side. This is not the case. It is slightly broken. And in principle, we reproduce calculations. Calculations reproduce the experiment pretty well. Here it matches, here it sort of matches, here it matches, here it doesn't match. We optimize the structure, we get something very different. And this is this funny side over here, this 5 coordinated side. So what's going on there? You can actually get that to match better. First of all, we look at this table where we now only look at the CQ for the aluminium. And here in this TBP, what you should get in experiment is 5.7. What we calculate for a relaxed PBE structure is 3.7. If we use CAN, we get 4.4. Still not so good. If we take the experimental structures, don't relax, we are much closer. So there is something subtle going on there. There is probably something like a subtle enharmonic effect or so. And how can we catch this? Well, we can catch this by sampling the temperature dependence of the thing, by doing a molecular dynamics simulation of the crystal, measuring the tensor and averaging the tensor. That's what we should do. That's not actually what we do. We calculate the time averaged positions as a function of temperature with the molecular dynamics. You can use machine learned force fields for that. How to do that is not at the moment relevant. That's a completely different story, completely different workshop. But when you do that, you get trajectories. The trajectories you can get average positions, and with those you can calculate again the tensors. And then you see you get much better. And while at 0 Kelvin you get 4.04, so on. But at 300 Kelvin you get much closer. You still are not at 5.7, but 5.3 is much better than it was previously. What you should actually do is calculate the tensor for all the time frames in your molecular dynamics run and then average over that. That is not what we did here, but that would be the actual proper way of doing it. Here you see it again summarized. This is the tetrahedral position. This is not sensitive to temperature. This is the non-tetrahedral position, the penta coordinate position that is very sensitive to temperature, and we can capture that with the MD. And then we went to the illustration with methyl ammonium lead iodide. And here you see a system where there is much more motion. That is nitrogen when it sits here, or maybe they almost change position. There are 4 in this tetragonal phase. There are 4 situations in between it is jumping. So it oscillates a little bit over here, and then it jumps to that orientation, and then it jumps in between. And when you go from here to here, the EFG tensor changes tremendously because it's rotated. Its orientation changes almost completely. So the principal axes are completely different in those 2 frames. If you would take the approach here, where you would take an average MD trajectory, what would happen? You would average this position with that position, with that position, with that position, and you would get that the whole methylammonium shrinks to one point in the middle of the gauge, which is completely unphysical. So that is a no-go in this case. In this case, if you want to account for the motion in your EFG spectrum, you indeed have to average the tensor for all the different orientations and then look at the principal components of that average tensor. And for methylammonium lead iodide, you can actually do that in a very cheap way. You don't have to do the dynamics. You know the 4 configurations that are possible. So you can just put your methylammonium like this. You press on the relax button and you let everything relax until you have a very stable minimum. And you can do it here also. Of course, it's degenerate, but it is rotated. So it's essentially the same calculation, but it's rotated with 90 degrees. No, more than 90 degrees. It's also mirrored in this case. And then you can calculate those 4 tensors in those ways. 4 tensors, you average them, and then you calculate from that your CQ or your VZC, so the components in the principal axis system. And that is how we modeled this tetragonal system over here. We did even a few more really dirty tricks over here. We even used the experimental information here. We know the experimental C over A ratio. We fixed that. We fixed many of the atoms. We also do dirty things with methylammonium and neighboring cells, but essentially fix the edges of this cage according to the experimental C over A ratio. And then we just calculate the CQ for a relaxed methylammonium and average over all 4. And then you get this curve from your calculation. And this curve over here with the black circles is what the experiment actually measures for CQ as a function of temperature. If you would do it statically, if you would only take this one, calculate this EFG only for that configuration, not average with them, and do the diagonalization only for that EFG tensor, you get a much higher VZZ, you get a much higher CQ. You get these numbers over here, which this is 0.6 and this is 0.10. There is a little bit of break here in the axis, so you get complete nonsense. And this shows that averaging is really crucial to get the right CQs over here. We still don't hit experiment here because we make many additional approximations. We fix the cage. We only relax one methylammonium given a fixed cage. That is a good approximation, but it is not the real system. We try to do it more carefully in the other system. That is where we now have also methylammonium. We also have lead, but iodide and bromide are a little bit mixed. So on the edges of the cell, here where all the iodides are sitting, now some are bromides, some are iodides, and we have this thing moving around. You can imagine that doing this trick we did for the pure methylammonium iodide, that is not working anymore. You would have to sample so many different configurations and hope that you doesn't go, because some of them are bromine, some of them are iodide. So then we want to do an MD, and we do a molecular dynamics simulation where this thing is actually moving inside the cage. But it has to flip very often. It has to sample all the configurations, and this is on the order of picoseconds. So you need a very long one. You need 100, you need 1,000, whatever picoseconds to get this right. You need even more. You can help yourself there with the machine learning. You can train a machine learned potential and then use that machine learned potential to really sample the MD trajectory over a very long time. You get very long MD trajectories. And then after a few thousand steps, you will find you have a real new configuration. And a few thousand steps later, you have a real new configuration. And for those, you can still do first principles calculations and calculate what the EFG tensor is. So you get a whole range of time frames, say a few hundred, over the whole range of the MD trajectory. very widely spaced, for which you do this EFG calculation again. You collect those tensors all in the same axis, just in the VASP XYZ system, and you average those tensors for one side. So for one nitrogen, you get this whole range, you average them. For the other nitrogen, you do the same trick again. For another nitrogen, you do the same averaging again. In this way, this at 64 nitrogens, you get 64 average nitrogen tensors, and you can calculate their distribution and compare that to experiments. And then finally, you get such a result. This is the actual experiment measuring the CQ from this build-up curve over. Well, this is for hydrogen. This is the build-up curve. No, the CQ is, and I shouldn't confuse two things. The build-up curves are for hydrogen. That's the orange curve. We should look at the blue curve. And we go to this point over here, and we can see what it approximately is. And then you see it is 137 kilohertz, this point over here, with a big error bar, of course. Oh, this is not the experiment. Yeah, the experimental error bar is rather small over here. That's the blue one. Anyway, 137. That is what we have to keep in mind, 137. And that is also where we approximately get. And this is in megahertz, so it's a factor 1,000 different. It's a factor 1,000 smaller. And these are just several ways in which we did the sampling of the trajectory. We have this number of configurations on the whole very long trajectory. So you talk at least 100 picoseconds. I don't quite remember how long it is at the moment. And then you can sample that with 1,000, 500, or 100 interval steps. And that means you either do a static calculation, you average over 37, 71, or 355, and then you refine in that way. And then you see over here, you see the same legend over here. You see that you get to something pretty decent in the end. Still, of course, this is not very beautiful because we have a sample here with only 64. So if you would calculate the distributions of CQs, this is the average value. And you would expect something like this famous check distribution, which is a distribution in the CQ you get whenever there is disorder in the first neighbor shell, which to a large extent here is the case. It would be better to have a little bit more nuclei again to have this distribution better sampled. But you see that it follows it pretty well. So hyperfine and zero field splitting. This is still something we have to talk about. This is not NMR really. This is ESR, EPR, Nussbauer maybe, whatever. And let's look at the EPR Hamiltonian or the ESR Hamiltonian. This is a similar thing, but you have nuclear spins. We already had them previously, but now you also have, say, local sites where there are unpaired electrons making a spin. Need not be a spin and a half, can be also something else, but these are localized sites. And then here you see the electron-Zeeman interaction. There is also a shielding-like tensor. Now it's the G tensor, which connects the spin of the electron side with the external magnetic B0 field. That is this one. There is something completely new now, which is called the zero field interaction, zero field splitting this gives, where is its D tensor, which is the analogous of what would be the electric field gradient tensor for the nuclear spins that you see over here. And here you see it now for electronic spins of electronic impurities. You see here the nucleus-Zeeman interaction, but now without the shielding. There is Gn over here, yes. You see, what is this J? This was the J cup. Yeah, this is again an exchange coupling between the spins. And here you see the nuclear spin talking to the electronic spins via a hyperfine tensor. And this, of course, has electronic structure information. This has. Here we neglect the shielding. This has, and this has. So it makes sense to look at these systems. This can be calculated, the G-tensor, but VASP can't do it. But there is a generalization of the G-pole that can actually do it also for the electrons. And if we would have some time, it would be nice to do this. So we will now focus on the A and on the D. The A tensor is the hyperfine tensor. So you have a big supercell with some defect species in it, whatever, where you get an effective electronic spin with some spin density distribution and an SZ expectation value. So it need not be spin and a half, it can also be something else. And then this tensor is calculated in this way. It has two components. It's dipolar everywhere, as you see from here, where the spin density, well, sits at the site of a nucleus and its surroundings. So R is the distance from where the spin sits to the nucleus. And there is a Fermi contact interaction where there is this delta function here. But this delta function is not a normal delta function, it's a kind of a smeared out delta function, which takes care of the proper shape of this density when you approach the nucleus. When you approach the nucleus, this density will diverge in the S channel. Also in the P and D channel, but in the S channel, it's much bigger. And that is somehow effectively accounted for in this whole term over here. That is this reference B over here. That is in this Blugel paper, you can read how this actually has to be done. When you do a calculation here, you have to switch on LL hyperfine equal true in a supercell, and you have to allow for spin polarization. I will do I spin equal 2. And then you get this reported. But there is also a core contribution to this, which is calculated separately. And it's rather funny. First, you do the valence calculation with the frozen core, and then you do an unfrozen core calculation with the frozen valence. And you have to add that by hand to these contributions over here. And again, you have to be careful with accuracy and convergence. The standard EDIF will not be sufficient. You have to play with that again. Be careful. To get this out, you need the chiomagnetic ratios here. Over here, you can just put it in, and you will get this out in the proper units in some kind of megahertz. But please see the wiki to see what this actually does. That's the hyperfine. The other thing you can calculate that is rather new, that VASP tells you that you can actually calculate this. That is the zero field splitting. This is a funny thing. If you have these spins, this zero field splitting, I just have to say, the spins in a magnetic system, in an external field, are pulled apart by the Zeeman, and that gives the splitting. But if you are in zero field, there is also splitting. And that is because there is a dipolar interaction of the spins with each other. And that is what the zero field splitting actually is. And the VASP implementation follows this reference. And you see, we have to calculate something dipolar. That's this form again. And we built now an anti-symmetrized wave function. That's the idea. Of the occupied alpha and beta spins. So we satisfy Pauli and calculate the expectation value of this operator. And then you get expressions that are Coulomb-like, like in usual Hartree-Fock, which are also indeed called J, and which are exchange-like. So you see here the exchange R1 goes to R1 and R2 goes to R2 in the orbitals. And that means that all the Hartree-Fock machinery that is present in VASP can be used to calculate this. In Hartree-Fock, you would just have the Hartree-Fock kernel in here. And now this thing goes in here, and you find your D's. I think it is symmetric. I'm not entirely sure. And I also think it is traceless, but this is also not entirely sure. To switch it on, you would switch on with this Incard tag. And then Hartree-Fock is automatically switched on. So Hartree-Fock is true then. But you don't want a Hartree-Fock calculation in general. You just want PPE. So in the exchange, that is killed again. That's all by default. So thus, you enable standard DFT. Of course, you can use an hybrid functional. You have to overrule this. But it also means that the calculation gets much slower because all these Hartree-Fock is switched on. Okay, when you do it, you switch it on, but then you take a single site with a few unpaired electrons in there with some effective spin in a sufficiently large unit cell so that it doesn't fill its periodic image. That's what you have to do. And you have to be careful with symmetry. And so you should apply the Hartree-Fock symmetry, not 1 and 2, but 3, where symmetry is applied in a different way, not where the charge density is symmetrized. So be careful. And you should only use the standard version of VASP, and gamma only doesn't work. And neither do non-collinear calculations. All these warnings are in the wiki, but I also say this now to you. You can have spin contamination here. And in the wiki, you see a way to suppress this, to work around from this. You have to modify the code actually to do this, but it is a very simple modification. And that is the Hyperfine story. Nuclear quadrupole interaction. That is this one. We already had it. This is just the field gradient story. And the CSA is ignored, of course. So we have to wrap up now. Two last things to say. Interfacing with external stuff. If you want to simulate spectra, you want to dump everything in a format that is suitable for that. There is this macros format, which will be supported in the new release of VASP, so that you can use the tools these people have made, the macros viewer, for example, to visualize the data. And that will be in the next one. But there are many, many visualization tools. For example, I want to point to this one, which is the local one from Nijmegen. That actually has been used to make a few of the pictures that you saw today, which you can also use. You can just use those fitting tools to simulate solid state spectra. That's one thing I want to say. The other thing I want to say, and that will be the last slide, that is the new features that will come into VASP. So we will have improved shielding output. You can still get the old one back, but you get a new one, which is controlled with this INMR print. And the 0 option is what you saw a few slides back. What will be new will be the macros. There is also the nuclear-independent chemical shielding that will be new. Here you see a nice picture. You can do that either for specific points or on a grid, but it is always only the plane wave contribution to the next that is there. Another new feature, well, it's not new, it was already there, is that you can actually look at the induced current density and make plots of the currents. Here, if symmetry is not supported. This is properly symmetrized. This you have to do carefully with not with symmetry options being switched on. And yesterday I talked a little bit about spin orbit contributions to the shielding. That should also be very soon be in the standard release. And with that, I hope this was interesting for you. And I want to thank you for your attention. And I want to go to the last slide, which says that we are now finished.